In this lesson, we're going to take a look at hypothesis testing using small sample size. And once again, what does that really mean? We're talking about sample size less than 30 in this case. Now, since we're dealing with a sample size less than 30, we are now going to be using a t-value from our manual, and it's actually a very specific t-table that we use, and it's Appendix it's Appendix D, the t-distribution for hypothesis testing. And the way this works is depending on whether or not you have a one or two-tailed test, you first figure out what type of test you have, and then you look at the level of significance. So if this is a 10% chance, or 0.1, 5% chance, 2.5% chance, and so on and so forth. Now, remember that this is the area of the tail, which represents the probability of making a type 1 error. That is rejecting the null hypothesis when you should not reject the null hypothesis. In other words, accept the null hypothesis. So remember that in terms of degrees of freedom, that's what we have along the left-hand side, and that is always going to be the n-1. So nothing's changed there. So, like as mentioned, we determine, first of all, one or two-tailed test, and then once we know which test it is, we look at the level of significance, which is given in the question, and then we determine the n-1 degrees of freedom, and then where those two different columns and rows intersect, that would be the t-value that we would use in the question. That becomes your critical value. Okay, let's try our first example. A survey of 15 larger cities in Canada finds the average commute time one way is 24.5 minutes. A researcher thinks the commuting time is actually greater than the reported figure. To help prove her claim, she takes a sample of 25 commuters and determines the average time is 26.1 minutes with a standard deviation of 5.2 minutes. At alpha equal 0.05, is she correct to think the population commute time is greater than the reported figure? Now, before we start this question, let's just analyze a couple things. This indicates that there is direction. It says greater than the reported figure. So we know then that this is going to be a one-tail situation. Now, the greater than indicates it's going to be on the right-hand side. It's pointing to the right. So first thing we're going to do is come up with our null hypothesis as well as the alternative. Pause the video, see what you come up with. So if you came up with a alternative hypothesis of the mean is greater than 24.5 minutes, and the null hypothesis is less than or equal to 24.5 minutes, you would have been correct. Second thing we're going to do is determine the critical values. And once again, let's put together the normal distribution. And it's going to look something like this. Based on our question, there's our normal distribution with the mean in the center. And the mean greater than 24.5 tells us then that it is a right tail, and since our sample size is less than 30, instead of a z here, we're going to put a t-value, and we're going to go find that out. Now what this is telling us is that based on the level of significance of 0.05, that's alpha is equal to 0.05, we're going to go to our table, and remember that we're going to look at a one-tail column, and at the 0.05 level of significance with degrees of freedom, 25 minus 1, which is 24. Okay, so let's go and make that happen. So once again, here's our t-distribution for hypothesis testing, and this is the level of significance. It's a one-tailed test at 0.05. So we know we're going to look down this column, and then we're going to look for degrees of freedom of 25 minus 1, which is 24, and where those two columns intersect, we end up with the magic value. So in this case, 1.711 is the critical value that we would put on our graph. So 1.711. So 1.711 is the critical value. Once again, if our test ends up being here, we do not reject. Our null hypothesis. If it ends up here, we do reject. Okay, so what we're going to do next then is actually do the test. In this case, we get the following. We use t is equal to the mean, sample mean that is, minus the population mean divided by standard deviation divided by square root of sample size. And let's put down what we know from our question. So based on this question, it says that our sample of 25 values gave us a mean of 26.1 minutes. Okay, so 26.1 is the sample, and our claim was 24.5 minutes. So the claim was that the mean commute time was 24.5 minutes. And then the standard deviation from our sample was 5.2 minutes. And the sample that this was taken for, now there are two numbers there, but our sample is actually 25. So you just have to pay attention to the detail. It says a survey of 15 larger cities in Canada. So this is the larger of the study, but our study chose 25 commuters. So this is the actual sample size. Putting this together, we get the following. And in this case here, because our critical value is now 3 decimal places, we're going to round to 3 decimal places. So 1.538 is going to be the critical value in this case. So fourth thing we're going to do is make our decision. In other words, plot where 1.538 falls on our curve and see whether or not it's going to be in the rejection region or not. So according to this, it looks like our point, our test value of 1.538 is in the non-rejection region. So our conclusion in this case, or our decision, is do not reject. Our null hypothesis. And then the last thing we do is, well, let's report our findings. What does this actually mean? And our final conclusion is that our sample data indicates the population mean commute time is not significantly more than 24.5 minutes. So once again, our final statement is based on H1, right? It's based on making use of this hypothesis here. So we do not reject H0, which means H1 is not true, and or we can't prove that to be true. With that said, I'm going to go to the next video. And remember, it's just, once again, the 5 steps. Nothing's changed other than the t value is going to be used for the critical value this time in these questions.